Let's start with a quick reminder of what serverless computing is. Serverless computing, at the end of the day, boils down to building and running applications without having to worry about server management. This layer of abstraction over the underlying infrastructure allows developers to focus on code, which improves their productivity and reduces the time to release new product features. In a serverless architecture, an application is executed to cater to a specific demand, no more and no less. If there's no demand, the application is scaled down to zero and no longer consumes resources. That means you get more density on your cluster because resource allocation is optimized when idle applications are scaled to zero until they are back in demand. That sounds amazing, right? So how can we adopt serverless architecture? This is where Knative comes into play. Knative is a Kubernetes-based platform for running serverless workloads. It is an open-source project that was started by Google in 2018 and is now a vibrant project on GitHub that is backed by Google, Red Hat, and many more. Knative consists of two components. The first one is Knative Serving. Serving is an event-driven model that serves the container with your application and can scale it to zero. So serving is kind of the implementation of the serverless definition that we've just talked about. The second project is called Eventing. Eventing defines a common infrastructure for consuming and producing events that will stimulate applications. So Eventing's job is to pipe events from third-party sources into our serverless application. Let's first explore the serving component of Knative. This is the component that gives us the ability to spin up a container serverlessly and then scale down to zero after being idle for a configured period of time. In Knative, a developer interacts with a higher order concept called a Knative service, which handles route creation, configuration, and revision management. To implement all of that, Knative Serving defines a few resources. First, there is configuration and revision. Now, these two are heavily tied together. Configuration literally represents the configuration that is needed for an application, like the image you want to run, the environment variables you want to set, and things like that. And a revision is an immutable snapshot of a configuration. So every time you change the configuration, it will generate new revisions. A route implements ingress traffic. A route implements ingress and traffic splitting. The route in this example directs 10% of the traffic to one revision and 90% to another revision. This allows us to easily implement canary deployments and different rollout strategies in general. On top of that all, there is the Knative service. Not to be confused. On top of it all, there is the Knative service. On top of it all, there is the Knative service. Not to be confused with the Kubernetes service. The Knative service is a top-level. On top of it all, there is the Knative service. Not to be confused with the Kubernetes service. The Knative service is a top-level entity that manages a set of routes and configurations. You may ask how difficult it is to migrate a Kubernetes workload into a Knative service. Let's have a look. On the left-hand side, you see a Kubernetes deployment YAML. This is a deployment. It has a name called front-end. We specify a label selector and how many replicas we want, and then we specify a template for the pods that we want to spawn, which contains the same labels we just defined in the label selector to connect both parts of the YAML configuration together, and then we define the container that we want to run. On the right hand, you see what the YAML would look like if we migrate that application into a Knative service. Note that I only needed to change the API version and kind to move to a Knative service deployment, which is very handy if you already have applications built on Kubernetes and want to migrate to a serverless architecture. I also don't need the parts highlighted in yellow. We can remove replicas and label selectors because that's handled for us in Knative. So we already have a more compact YAML file. But note this, a Kubernetes deployment object is not enough to have a working application. We still need to define a service and an autoscaler to make the application cater to high traffic requests. While on the Knative side, that is all handled for us out of the box. So really a simple yet powerful deployment framework that is very easy to migrate to from a Kubernetes deployment. Now let's take a look at Knative eventing. Remember we said two components. Now let's take a look at Knative eventing. Remember we said two components. Knative serving was the first one, and now we are looking at Knative eventing. Knative eventing provides the tools that allow us to route events from producers to consumers. Those events are based on the CNCF standard called Cloud Events, which defines a common format for events that can be understood by heterogeneous systems. The simplest event pattern is a source to sink pattern. An event source is an adapter for integrating external event producers with event consumers or sinks. The event source transforms events from external systems to a cloud event before pushing them onto the sink, which is typically a Knative service. A Knative service, as you remember, manages the configuration and routes of our serving component. The source to sink is a simple pattern with some obvious drawbacks. For example, there are no queuing or filtering capabilities, and this pattern can only support only one sink at a time. A more flexible and powerful pattern is the broker and trigger pattern. Here the event source uses the broker as its sink, meaning it becomes the target of the event. The broker then will take these events and dispatches them to all sinks which are interested in this specific event type. To express interest, a sink subscribes to a broker via triggers. And the trigger itself can have a filter expression that allows us to dispatch only certain events to our sinks. So with the setup, we can dispatch and filter events to any number of sinks. OpenShift Serverless, which we will use in today's demo, is based on the Knative project. It packages all the goodness that comes with the Knative project in an enterprise solution that is supported by Red Hat. Now, before we jump into the demo, let's spend a few minutes to explain the context. The industry we chose for today's demo is the gaming industry. Not just because it's an industry that's dear and near to my heart, but more importantly, last year, the revenue from the gaming industry exceeded that of sports and movies. Last year, the revenue from the gaming industry exceeded that of sports and movie industries combined, which just shows you which just goes to show how powerful the gaming industry really is. So what can disrupt this industry? Cheating. Game cheating has a huge impact on the gaming industry. A survey showed that 77% of the impacted players are likely to quit playing a game if they have a negative experience against cheaters. And obviously those players are less likely to buy in-game content. So there is a real economic impact on the gaming industry. With that in mind, let's see how streams and serverless can help protect our players from cheaters. The game we are going to try and protect is Battleship. Our game is going to generate events that are written to a Kafka stream. The rest of our components will run on a dedicated OpenShift environment that is linked to our Kafka cluster running on an OpenShift serverless environment. An audit service runs on the OpenShift cluster as a serverless function. The audit service analyzes the events coming from our game and identifies and flags suspicious events. For simplicity, we have set a rule to flag an event. For simplicity, we have set a rule to flag an event for cheating if it contains more than 10 hits. A Kafka event source reads the events from Kafka topics and forwards them to the other. A Kafka source reads the events from Kafka topics and forwards them to the audit service. The audit service will emit a new event if it suspects a player is cheating. This new event is routed to an email serverless function that notifies the game. This new event is routed to an email serverless function that notifies game admins about the suspected cheater through a broker and trigger pattern. Okay, before we start, let's take a look at the prerequisites for the demo. And you can check this Git repo for all the steps you need to reproduce the demo using this bit.ly link, so ship horse cheat detection. And what we'll need is access to the Red Hat console and access to the OpenShift developer sandbox. And then we'll need to install 3 command lines, the CLI for OpenShift itself, and the Red Hat OpenShift application services CLI, and the one for JQ. And JQ will make it much easier for us to extract data from a JSON file. And finally, I'm using SendGrid as my email platform. Okay, the first thing we want to do is head to the OpenShift Streams console. And OpenShift Streams gives you access to hosted and managed Apache Kafka clusters. I'm going to use here a limited trial instance, which will remain available for 48 hours. Now, let's create this Kafka instance and give it a name, like Ship Wars Cheat Detection. And let's select a region and create our instance. You can see creation is now in progress. Once the Kafka instance is created, we now want to link that instance with our OpenShift environment. So I'm going to head over to my OpenShift developer sandbox environment, choose add from the side menu, then scroll down to the manage services option. I'm going to select my Red Hat OpenShift streams for Apache Kafka. Connect. We want to connect to our Kafka instance that we created on OpenShift streams. Once I select next, we're going to see that Kafka instance in our topology view. Also, a service account was created for that purpose, but we still need to grant the service account permissions to allow it to produce or consume events from our topic on the Kafka instance. So I'm going to get the service account ID from an OpenShift secret and store it in an environment variable. And then I'm going to log into my OpenShift Streams account, select the Kafka instance we created at the start of this demo. I'm now going to create a topic called shots. And finally, assign permissions to my service account. Looking back at our design, if you remember, our serverless audit service used a broker to emit events that contain the audit results, and then downstream services like the email service can register their interest in those events using a trigger and process them. So the next step is to create our broker. Now, if I go to my topology view and move to the administrative perspective, there is an option for serverless, and it's divided into serving and eventing, like we discussed earlier. And so if I go to eventing and then brokers, create a new broker from a YAML view, and I'm going to paste a simple YAML that we will use for this purpose. And then create the broker. Now, if I go back to my topology view, we will see that the broker is indeed created. Now the next step is to deploy my serverless functions, and we can obviously do that from my developer perspective. So I can click Add and paste the image name here. We can select a serverless deployment option, which also allows us to configure the scaling rules. So things like the minimum number of pods, obviously we want that to be 0. So when the service is idle, we can scale back to 0. And the maximum number of pods we want to allow our service to scale up to. The maximum number of concurrent HTTP requests we want to allow for our instance, and the utilization that we will allow before we scale another pod. This is one option, but what I'm going to do here is apply my configuration using YAML files. Here's the audit service. And then the email alert service. This will spin up two services in my topology view. As we can see here, the cheat detecting service and the audit service. Now, if we look at our architecture from the slides one more time, the next piece of the puzzle is the event source. So let's go ahead and create it. We select Add from the side menu, and we want to add an event source, specifically a Kafka source. I'm going to click Create, and here we have a nice wizard to help us provide the input. I'll first provide the Bootstrap server. This is the linked Kafka cluster we created earlier. And then I will add a topic called shots. I want to receive data from this topic. And our consumer group is called Knative consumer. We also want to enable SASL. So this is where we use our service account details. To provide our client ID and our key. We also need to enable TLS. And finally, we want to direct the events from our shots Kafka topics to our cheat detection service. And we go ahead and create our Kafka source. As we expect, we will see that being created in our topology view on OpenShift. And finally, I'm going to create the triggers using a YAML file, which as expected immediately gets reflected in our topology view. Now, instead of actually playing the game, I'm going to simulate traffic with an application we created just for this purpose. Now, as you can see, my other service starting to scale up in response to the requests, and it's looking for a cheat rule. Here we've set up the rule to look for a number of hits that's unrealistic. So a player using 10 hits at a time, for example, and then it's going to trigger an email notification. And that's exactly what happened. So the audit service detected that the player made 23 shots at a time, which is considered as cheating. And it invoked the email notification service, which then sent this email to my account. And as you can expect from a serverless architecture, my application starts to scale down once it becomes idle. So we've seen an end-to-end
architecture where we've leveraged both streams and a serverless architecture to implement a cheat detection solution.